Welcome back. This is the first year we've ever had to deal with the idea that that we don't have like one day left after holidays, 2 weeks, so we're not anywhere near being done yet. You still have one major lab assignment. You're going to get that on Thursday. It'll last for 2 weeks. And we have one more major topic to deal with in my part of this course, which is sequence stratigraphy. And this is, in many ways, the most important thing that geophysicists are doing across the spectrum right now. This is the type of thing that is has buzzwords in it. If you plan on interviewing for anybody that deals with anything petroleum, you better be at least familiar with some of these concepts, at least enough to bluff. And when I say bluff, I mean that seriously. Nobody will fully understand this ever in their lives. Even if you're working for the oil companies, they don't fully understand it either. The reason for this is that as a science, this is evolving right now, and there's still a lot of ground truthing to be done on it. So today we're going to start talking about sequence stratigraphy. Sadly, and for those of you that like to be challenged in terms of stuff and get applicable stuff in the labs, I have nothing I can give you in the labs for interpreting sequence stratigraphy. Because frankly, you really need to have high quality sections, and we just do not have them. If and when you do get the opportunity to go into petroleum, I encourage you. In fact, I don't even have to encourage you. You'll be forced to take as many short courses as possible. And that's where you'll get these priority things where they will be stuff that comes right out of the oil companies. You look at them and you surrender them right afterwards. You're not allowed to take those things out of these short courses because they are almost top secret in some ways. The more you learn on this, the better you're going to get at interpreting things. But you'll never, if you're like me, you'll never be fully comfortable in doing this whole thing. And I published papers in this area, and I still really don't know what I'm doing. Damn, we shouldn't have that recorder on right now. Last time we met, we were talking about sonic logs. This was just a recap in terms of familiarizing you with how things worked. We talked about synthetic seismic profiles again, just to give you again a little bit of background. And then we talked about Peter Vail towards the end. Reminder also, we introduced some new ideas, not introducing new ideas, but just talked about them for the first time. We talked about side scan sonar, which is just a type of geophysical device that produces pictures that are almost radar images of what the seafloor bottom looks like. This is a very interesting way of looking at the seafloor bottom, and of course it has practical applications in industry. These, if you recall, are iceberg scours off the coast of Newfoundland, which this is important stuff if you're trying to figure out where to put a pipeline. And I'm not sure if I fully explained this to you, but these scours were eventually determined that they actually were not active, that they were probably associated with scouring when sea level was lower, so they might be 8,000 years old. And it gives you an idea that what you're looking at here now are really, really old seafloor things. And they're big, too. I mean, these things are several hundred feet across in some cases, so you've got to worry about the scale a little bit. We talked about some of the high-tech sonar techniques that have been developed, and again, if you can manufacture a market in some way, you can make money off of these things. Although in some cases, if you're dealing with really big-ticket items, it's only governments that can afford to do it. So we talked about Gloria, which gives you these incredible swaths. I mean, doing 18,000 square kilometers a day, but of course the resolution is way off. You get a picture of the seafloor bottom looks like this, but at 50 meters resolution, you'll miss things 150 feet wide because it doesn't have the resolution. So if you want more detailed stuff, use Toby. And Toby can give you some really nice little bottom profiles. This is largely academic in nature, or if you're looking for major surveys to try and figure out what the seafloor bottom's got on it, for resource management, etc., you can do it. But for the most part, nobody is going to be doing this type of thing because it has no real economic potential to it, except for mapping out your territory. What is important, however, is being able to understand how waves travel through rocks at a smaller scale so that you can actually apply it over a large area. So basically the jump from well logging, where you do stuff like we've done previously, to seismic interpretations needs to have some sort of means by which to match up what seismic character would be in rocks to what it will be over a larger area, as we're going to get into now. All right, so we use a sonic log to do this. This more or less measures how waves travel through rocks as you're pulling them through the well. Ultimately, this is going to give us things that look like this, or at least allow us to link the wells to profiles that look like this. And it was important, again, that we remind ourselves that what you're looking at here are reflections. And these reflections are driven by contrast in the rocks as you go into the Earth's interior. Okay, so every time you see a dark line on here, it's telling you that there's a change between the rocks above and below those surfaces. And ultimately, the thing that controls that reflection, or the reflectability, is going to be the acoustic impedance, which is a combination of the density and the velocity of the waves traveling through the rocks. Okay, so ultimately, this is the math that controls whether or not you're going to get a strong reflection or a weak reflection. And this is what we did math-wise in the first lab that we were together, etc. Okay, and at the time, you didn't really know what it was all about. You probably still don't remember any of it, but the main thing is that you're dealing with this type of aspect. And because this is ultimately what you're going to be getting are seismic lines that look like this. So we can take this over a large area, we can start looking for reflections, we can look for reflectors, and ultimately we need to know what the characteristics of each of the rock units are in each well to be able to trace these reflectors along. So if you know that at this site here, the red reflector happens to be the base of the Jurassic, then you can follow that reflector to new areas, always assuming, of course, the character of the reflector there and here means it's the same reflector, and you can actually start making some determinations about how the bedding and how the rocks shift from one point to another. And remember, the beauty of using seismic lines like this covers a large area relatively cheaply, allows you to expand your surveys to larger areas, etc. Okay? Then we introduce this guy, Peter Bell. And, you know, I didn't go into much detail about him. As I said, there's whole books that have been written about this guy. But you have to remember, he's the inspiration for kind of crossing the bridge between pure applied petroleum exploration and academia. Because he saw that if you figured out how to read these logs, you can more or less start looking at worldwide relevant changes to academia. And of course that dealt with sea level change. Okay, we're going to come back and talk about sea level change in a minute, but we also have to start introducing what sequence stratigraphy is all about. This is the basic concept. There's a lot we have to talk about. Okay, so between now and Wednesday's lecture, we're going to introduce stuff that will make you seriously dangerous in an interview. If someone starts talking to you, you're going to start hearing every... If you remember the Charlie Brown cartoons, you know, where Charlie Brown, the kids would always talk to each other, but the parents always went, wonk, 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 wonk. All right, now picture yourself doing this, all right? You're in an interview, and they're asking you how you're doing, how are your classes, and then you're going to say you did geophysics, and they're going to say, oh, in your geophysics class, wonk, 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 TSTs? And you're going to go, what did he just say? Or what did she just say? And you're going to have to tentatively go, yes, and pray to God that you're not saying that you know something that you don't really know. Because the next question is going to be wonk, 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 without any help whatsoever. This stuff is really annoying because it is loaded with jargon. And that's the real issue on this. If there wasn't so much jargon, if we didn't have shortcuts in terms of condensing everything, it might be something that was easier to grasp initially. I've done about 3 short courses on sequence stratigraphy in 3 different countries. And every time I'm sitting there listening to them, everything sounds like it makes sense, everything's going well, and then all of a sudden, I start hearing wonk, 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 and I'm in the same situation I was when I was in the classroom. All of a sudden, I start to lose it a little bit, okay? Anyway, I'm going to try and give you the basic stuff that will make you dangerous, as I said, in interviews. We're going to talk about systems tracks and what types there are, and ultimately how it has application to sea level change. And I don't think that's necessarily in the right order. I was twisting things around over the holidays in terms of how I was going to talk about these things. So anyway, let's start off with the Vail curve again, because that's where I left you hanging. So that, you know, Peter Vail comes up with this idea. He's working for an oil company, and then he takes it to the next step where he starts talking about how sea level change works around the world. All right, so this introduces the Vail curve. Now, once again, for those of you who have not had stratigraphy yet or have not had a chance to think about this from the large-scale side of things, when we look at the world, one of the most important things we have to look at in terms of Earth history is how things change over time. All right, so the idea that sea level rises and sea level falls is very well established. But have you ever asked yourself, how do they quantify that? Oh, I mean, yeah, you can go to the middle of Wyoming. And in the Cretaceous, find that you've got sedimentary rocks that indicate marine sedimentation everywhere in Wyoming. But how do you know that means that the world sea level was high and not just that the continent of North America was sinking? Because we do know continents rise and fall in various places. There's tectonics going on. For all you know, the tectonics of causing the Rockies to be pushed up is causing the central part of North America to be depressed. That's not an unreasonable interpretation of things. What you need is to have a worldwide curve that is purely free of any local influences. And the only way you can do that is if you can literally compare rocks around the world at the same time and see what's going on. And the arguments are, if everywhere around the world you're getting an idea that sea level is rising, it's probably a worldwide or eustatic curve. If everywhere around the world it starts to show that sea level is dropping, it's a worldwide drop in sea level. You can determine worldwide transgressions and regressions if you had some sort of ability to actually look at all the world's rocks at the same time. And here's where Vail really saw the practicality of this. He was sitting on all these seismic lines that Exxon had. And Exxon is a major player. All right, they had seismic lines around the world, and they had been interpreted. They had the ability to say, here was the base of the Jurassic, all around the world, and look, isn't it amazing that we start seeing evidence of sea level rises all around the same time? So that's how you could come up with a worldwide sea level curve. Now, I did tell you at the time that this was being done, a lot of the initial criticism was rightfully pushed on this whole idea that Vail did the interpretation based upon material that nobody else could see. So there was no way to have independent confirmation that his curve was correct. Okay? Nevertheless, after a while, as more people did this, and everybody jumped on the bandwagon. I mean, they jumped on this bandwagon as much as we jumped on the plate tectonic bandwagon once we came up with the evidence to suggest it had to occur. So since this was going on in the 80s, we'd have a lot of evidence coming in to more or less come up with something that looks like this. So now this idea of a worldwide static curve is fairly good. It's fairly cool. And of course now we're getting down to the point where we can actually do some pretty detailed stuff. Now this is not the detailed stuff. The detailed stuff is when you look at this interval through here and start seeing changes that are going back and forth on the order of a couple million years. But I throw this in now to show you that the whole idea of sea level change is dominated by cycles. All right, so when you look at sea level change, it does this, then comes down like this, etc. You're seeing the broadest scale cycles because this covers the last 600 million years. Up close and in detail, you'll see that there's a lot more cycles taking place on this. The Vail curve, used to see in general, does not come up for an explanation as to why sea level is rising and falling. That is what requires interpretation from the academic side of things. We know that there are first-order changes, second-order changes that take place over hundreds of millions of years. These things are largely thought to be tectonic in nature, the idea of the continents moving around. Every time a continent comes together, if you go from two isolated continents, bring them all to one larger continent, what ultimately is going to happen is you're going to change the amount of rock mass in the seas, and you're going to see sea level starting to drop down dramatically, relatively speaking. But when the continents all break up, like happened in the Cretaceous, all of a sudden you got a lot more continents moving around. You have a lot more oceanic crust between the continents. In much the same way as throwing a bunch of bricks in the bottom of a bathtub is going to cause sea level to rise, you're going to get large-scale sea level rises when that occurs. But think about tectonics. It's slow-scale stuff. That's why these broad-scale things, which are by far the most dominant sea level changes we get, take place over such a long period of time. Now the smaller scale changes, third, fourth, fifth, and sixth order changes, and sixth order changes go down to about 10,000 years. All right, those changes take place too rapidly to be done by tectonics. And of course, this is where Milankovitch cycles come in, the whole idea of orbital eccentricity and changes like that. Okay? All of this stuff is working simultaneously, and the Vail curve has the potential for resolving all of those, even down to the fourth, maybe the fifth order changes. Yeah?
So is the Vail curve just a major, the big is one that...
No, it's the sea level curve. It's the whole thing. It's eustatic. It's a whole world thing. But it's up to us to determine what are second order, third order, fourth order curves.
So he didn't come up with the first, second, third, fourth, fifth order?
He came up with a sea level curve. But what was actually called, I mean, by this time we knew about Milankovitch cycles. So they knew what was actually controlling some of these packages. But they didn't go into the details. That's where academia came into it, okay, where you start looking at the rocks and see how these things are matched. But once you know to look for these things, once you know to start finding them, you'll find cyclicity even within a sandstone that was shelf-derived. You can see cyclicity if you look for it enough, okay? All right, so this is what happened. They came up with this curve, and all of a sudden everybody's jumping on the bandwagon. All right? Even the paleontologists are jumping on the bandwagon for this, because by looking at how sea level is changing, of course, you can start to determine how things have occurred, how to interpret paleontological changes in the rock record, etc. Okay? Why is this so important? From the petroleum and sedimentology point of view, it has to do with what sea level does for sedimentation. Okay? It controls where the most sediment is going to be deposited. If you think about it, while it's true, rivers will be flowing on land that don't really care too much about what's going on at sea level, at least in the interior of continents. The vast majority of sediment that's going to be produced is going to be produced along the coastal plain and the shelf, because that's where the rivers dump into things, okay? So you've seen this diagram before. You saw the idea that we have sediment coming in from the rivers, coming into the shelf area, coming into here. What we didn't talk about was this, accommodation space. That's one of those buzz concepts that in hindsight is ridiculously easy to understand, although in terms of when it was established and when we actually started talking about it, it really wasn't until after this whole idea of eustatic sea level curves was proposed that we did think about it. What is accommodation space? It is basically the space that you can put sediment in. And accommodation space is going to be controlled by where sea level is. If sea level drops, all of a sudden you don't have the accommodation space you had before. Net result is you don't get as much sediment being produced. If sea level rises by, say, 150 meters, all of a sudden you've got the potential to put 150 meters more of sediment along this depositional environment. Anybody care to speculate why the petroleum industry was really pumped by this whole concept? All right? What are you looking for? You're looking for reservoir accommodation space. If you got a good body that is capable of producing or storing oil, it's a lot better to have a thicker body than a thinner body. That's why they were interested. That's why they more or less bankrolled this whole concept of looking how sea level affected things. But it affects everything we do in terms of sedimentology, stratigraphy, everything if you think about it. It's an underlying concept. Now, this is where you have to start understanding how this is going to work in the grand scheme of things. Diagrams like this are absolutely standard in sequence stratigraphy analysis. What you're looking at here now is how accommodation space affects the packages of sediment that are being produced. Not where the beaches are, not where the deltas are, but where whole systems are deposited. So start thinking now about fluvial systems, which would include lakes, rivers of every description, possibly the upper part of deltas. Start thinking of shore-face systems, beaches, deltas, estuaries, all as one big package. Start thinking about the shelf itself, oolites, muddy shelves, reefs, and the off-shelf stuff at the base of the slope, submarine fans and various types of deposits like that. Don't start thinking narrow-minded about a small little delta as being this whole thing. It's the whole frigging shoreline. So as you go from Mobile Bay all the way to Florida and Texas, that whole strip of shallow sediment represents the shore face. The inland part, the fluvial part, take it as far inland as you want to go. That is the fluvial system. The idea now is that if you've got sea level at one point here and then all of a sudden you raise it, what you're going to do is shift where the deposition is going to take place towards the interior of the continent. As sea level rises, sediment is shifted in towards the interior. But now you have the ability to start filling in this space with more sediment. But what's going to control the type of sediment that's being produced is the balance between the rate of sea level rise and the rate of sediment coming in to fill that region. Everything is at equilibrium. All right, so what you have here now are three different situations where you have three different balances of sea level rise with sediment. This first one shows you what happens if you have a sea level rise with a very low sediment flux, meaning little sediment's coming in. This would not be our part of the shoreline because we actually have a fairly high sedimentation rate along here. But there are plenty of places where if you have sea level rise, what will happen is the sediment can't keep up with the sea level rise. In a situation like this, you end up getting this backstepping phenomenon where you have shelf or shore face environments with these deeper water environments kind of stepping backwards like so. This is a classic transgression, what you would call as a transgression. In other words, it's what you would predict. Because sea level is rising, you would expect the sediment to move backwards. That's not always what happens. If you have a situation where sea level is rising, where the sediment flux is consistent or matches up with what sea level rise is doing, what you end up getting is something that looks like this, where there might be some backstepping, but for the most part you actually see the shore face and shelf environments more or less staying put. But what you end up getting is a stacking up phenomenon. There's your thicker sequences separated by boundaries between them. Now again, I want to reiterate, this is not the beach, this is not the shelf. These are whole systems that consist of beach deposits, maybe some pluvial things in them, really thick packages. You don't see why this is so relevant to our discussion on seismic stratigraphy yet. These are all surfaces. These are all surfaces that consist of different rocks that will give you good reflectors. In other words, this is the type of stuff that you can resolve from a seismic section in order to come up with the whole concept of accommodation space and sea level rise in the first place. That's what Vail had to deal with. Those are the diagrams he came up with, and from this, you're capable of actually determining what sea level is doing. The last one is where you have sea level rise taking place, but you have a very high sedimentation rate. Net result here is you get the effects of a localized regression. This is what would happen today. This is what is happening today as sea level rises, which it is doing, when you have the Mississippi Delta right in your neighborhood, which is producing more sediment in the area than sea level can actually keep up with. We will continue to have a regression in the Mississippi Delta region while sea level rises. As we're flooding Florida, the Mississippi Delta is going to continue to expand. See the issue here now? Not only do you have to worry about tectonics, you have to worry about the local sediment influx. But again, if you've got enough sequence stratigraphy stuff, if you've got enough seismic lines, you can actually start resolving these differences by comparing them side by side. Pretty cool stuff. If you can turn off, and this is where I have difficulty, you've got to be able to turn off the small scale stuff. You can't look at this and start considering where's the beach. You cannot do that. You have to look at this in terms of the whole package. This introduces the concepts of systems tracks. And systems tracks are going to be controlled by the nature of the sediment, yes, but also when deposition is taking place relative to the sea level curve. All right, so systems tracks are linked to sea level. And that's where the jargon really starts to get to be rather annoying. Okay, so by the way, I should have mentioned this previously. If I haven't done it before, let me again remind you. If you see anything in red, make sure you know what that is, because that's where test terms are going to be coming from. Yeah.
So on the previous slide it said sea level high span. Is that?
Wait for it.
The same thing as
Just wait for it. All right? Speaking of which, so how are the systems tracks actually named? It's according to where sea level actually is, okay? There are numerous systems tracks, and this is where things get progressively more annoying, because every single month it seems like someone comes up with a new systems tract. The 6 most important, at least in my humble opinion, are identified here. Their names are condensed to these things. And this is why you have to be aware of what an LST is, what HST is, what a TST is. I will ask you this on tests. LST stand for Low Stand Systems Tracks. HST stand for High Stand Systems Tracks. TSTs, Transgressive Systems Tracks. FSSTs, Falling Stage System Tracks. RSTs, Regressive, and RSTs, Forced Regressive Systems Tracks. Now let's talk about what the names themselves are implying. Low stand, high stand, since that's a question that was asked previously, has to do with the relative position of sea level. So, if you're dealing with a low stand, you're dealing with sea level at its lowest point. If you're dealing with a high stand, you're dealing with sea level at its highest point. Transgressive is when sea level is rising. Regressive is when it's falling. Now, a couple of these other ones here, the falling stage and the forced regressive systems tracks, we'll talk a little bit more about those in Wednesday's lecture. You will see, normally, when people are talking about this, they draw a curve that looks like this. And this is a very common thing that they will put associated with their interpretations. At this point here, they will refer to the high stand systems tracks, where you basically are at the top part of the curve. Down here would be the low stand systems tracks. Obviously, what you're dealing with here now is a rise in sea level versus a fall in sea level. The transgressive systems tract represents this, and the falling stand systems tract represents this. Where these other ones come into it is when you're dealing with different amounts of sediment inflow. That's separate from a regressive systems tract, which is falling because of sea level. Okay? Now, if all of you are sitting here going like, oh my God, this is going too fast, deal with it. All right? This is, as I said, the rate in which this stuff was produced in literature. We all had to deal with all the stuff just being sent out there. But ultimately, these things will control where sediment is going to be deposited and the nature of the sediment that's going to be deposited. Consider again, if you got sea level at a certain height, you've got systems being developed, you've got beaches over here, you've got shelf over here, you've got the deep marine stuff over here. Deep marine stuff, incidentally, is usually going to be what? Fairly muddy, not particularly good reservoir rock. If you drop sea level all of a sudden, you're still dumping sediment in the deep marine environment, but now what kind of sediment is it? The shelf stuff, porous stuff. Then sea level comes back up, you start dumping muddier stuff off the side again. So looking for these deep marine environments where there's the potential of reservoir quality sediment is a major thing that we're doing now. This is one of the reasons why we're drilling in deep water environments right now, is because we have an idea as to which deposits are going to potentially oil or gas producing. Right? We've already used this to interpret things. Right? So these are the systems tracks. Now for today, what I'm going to do is I'm going to try to talk you through some of these. Actually, I'm probably just going to have a chance to talk about the LSTs and the HSTs. We'll come back and talk a little bit more about these in Wednesday's class. The main thing again to note here is that you're talking about periods of time that are locked to sea level position and what's going to be produced of that. All right, low stand systems tracks. Here's the official definition. These are deposits that accumulate after the onset of a relative sea level rise. Now that may sound counterproductive and all that, all right, but this is when sea level is just starting to come back up, okay? So this is when things are being produced just before that rise starts to take place. Let me talk you through this as best I can, okay? Here is the position of sea level, okay? So sea level is right at that point, okay? And it's going to start to rise at this point here, okay? So there's the start, and there's where the end of the regression is going to be. So this is where we're talking now about this point right there, where sea level is just starting to rise. At this point, you're getting most of your sediment is being deposited at this point here. That's where the shore face is, all right? So there's where sea level is. This would all be above sea level. At this situation, you're going to have fluvial deposits, maybe some estuaries, a lot of down cutting, okay, because base level is going to be cut down this point. So in other words, all the stuff that you see being deposited here would be equivalent to river deposits or fluvial non-marine deposits. There's your shore face sediments, beaches, deltas, etc., and then it grades off into what would be the equivalent of shelf-type sediments in deeper water. This would eventually grade, incidentally, into deeper water stuff. At this depositional environment, okay, you have a slope that is pretty steep because basically you're depositing off the edge of what would be the slope. You get very thin packages of sediment that change the character relatively quickly. So shore face here getting deeper and deeper and deeper. All right, so there's your package of sediment linked to these fluvial deposits that are here. Okay. One of the things that's really important, and certainly for interpreting, because this is easy to spot, is that these low stands systems tracts will fill in erosive and scoured surfaces. In other words, it's not unusual to see this type of contact where you end up having coarse grained material, incised surface, all right, as base levels drop, depositing things like conglomerates and sands on top of them. Okay, this is important because a surface that looks like this, incised valleys, these things are relatively easy to spot off the seismic lines. In fact, it's easier to spot these things than anything else when it comes down to interpretation. In fact, it was this surface that Vail used as the starting point of each of these oscillations. He called these sequence boundaries. And in the jargons of petroleum, SB. So on some of these plots that you see, you'll see SB1, SB2, SB3, SB4. Each one of these is a bottom of a low stand systems tract within a vertical series of these things. All right? All right, now the question you should be all asking is, this is wonderful. This is cool. How the hell do you do it? This is where I can't help you too much because I have never in all my days ever actually interpreted one of these things from the sequence stratigraphy point of view. Well, I've done the short courses. I sat there with my pencils, much like you were doing the other day, tracing things out and finding stuff. But I've never had to try and link a sequence boundary in the work I have been doing. Okay? We just assume that everybody else knows what they're doing. It has to do, again, with the nature of the reflective surfaces that you're dealing with. Okay? What you look at now is the pattern that you get for all these different beds that represent the sequence tracts being piled on top of one another. We call them stacking patterns. You're going to see the term backstepping, onlapping, all these things that are in here. And it has to do with the nature of the way the contacts look. All right? And again, this is a lot of jargon. Of these, the most important term of all is the term clinoforms. Clinoforms are layers within packages that might look like this. All right? Now, when you did your little introduction to seismic interpretation, you saw some of these packages. What you're looking at are sub-parallel reflections that cut across the normal horizontal layering that you would expect. In this case, this represents a depositional system. It's a prograding system of sediments being added. Now, that prograding system is thick. It's on the order of several hundred meters in thickness. So it's not just a beach, it's not the end of a delta, it's the whole, basically, shore face that is advancing from the shoreline out into deeper water. That's the type of thing you get if you raise accommodation space and you literally start having the deltas and beaches migrating more seaward. So this type of clinoform packaging is what we're going to be talking about in a second, and the nature of which, how those different layers actually relate to the clinoforms themselves is either going to be one of these things. And that can also be interpreted in terms of which way deposition is going. Okay? Before we do that, I want to again reiterate, I can't do this. And I doubt very much whether you could do it, even if you were working on this for several years, until you get the experience to go from this, which is the basic sequences that are the seismic stratigraphy we talk about, to this, where you can actually interpret each of these layers as being different things. Each one of these terms here refers to either a transgressive or a high-stand systems tract that someone has interpreted based upon the nature of the cliniforms. And that's what they're dealing with. All right? I don't know of anybody who can do this at this point. For most of you, it's not going to matter, at least not initially, because you're going to be assuming that it's already been done, or not going to be assuming, you're going to be using charts that have already been done. So you're going to know where sea level was, relatively speaking. It'll be up to you to interpret which one of the sequences you're dealing with are high stands or low stand system tracts based upon the Vail curve that's been established now. But as I said, that takes a really good geophysicist to go from one of these steps to another. And I am not one of those people. All right, I did mention, however, that there's going to be different types of cliniform patterns, and here they are. This is what the terminology is all about, okay? So, again, definition from cliniforms: parallel but inclined surfaces. You've seen some of these before, all right? There's that one there, the classic type of thing. Now, this is called downlap. Downlap is where you actually see the layers starting to kind of get more acute as they make it towards the bottom. This is classic progradational. In other words, it has to deal with stuff that is moving in this direction. Onlap is when the cliniforms actually come up in this direction. That's the type of pattern you get if sea level is actually reversing itself now and sediment is starting to be deposited back in this direction, like so. So this stuff is younger than this stuff is younger than this stuff, but it's backstepping in this direction, like so. Okay? And there's a whole bunch of other types of patterns, truncations, etc., that have to do with, again, interpreting what kind of systems tracts you're actually dealing with. So these are the patterns that you need to be able to interpret if you're going to be doing sequence stratigraphic analysis, etc. All right? Let me show you what some of these things actually look like. Here again is the pattern of stuff that you see. Okay, so that's downlap. And these are, they call this base lap. Again, the jargon is really annoying here, okay? Base lap refers to these two things where you're talking about how actually they come in contact with the bottom surface. This is an example of downlap. If you look here, you'll see the this is really greatly enlarged, obviously. So here's the cliniforms coming down like this, and there's the downlap surface. You see it truncates like that. This one comes down and truncates like that. Steeper here, becoming more acute as you get towards the bottom. And there's the actual onlap surface right there, okay? Now it's actually, you know, when you blow something up like this to show things in detail, it's actually harder to see this as being cliniforms than if you looked at it in a smaller type of package. In fact, if I had my way, I would have, if I was doing a slide like this, I would have had an inset showing you where it came from, so you can actually see the larger scale things and compare it to the smaller scale. Okay, so this is an example of downlap. This is an example of base lap. In this case, it would be this type here. Okay, and you can see how it comes up like this and truncates right along that surface, like so. Vlad, no offense to you and your countrymen or anything like this, this is an example of what's affectionately known as Russian geology. It's what the Russians are notorious for in their when they do geological publications is they'll show you an outcrop and they will mark up where all the contacts are to the point where you can't actually see the outcrop anymore. All you see are just the markups. And of course, you can't actually see what it is they're trying to show you. So what we would do in North America is we'd have a picture of what the original outcrop looked like, and then there'd be an interpretation or a sketch underneath it that shows you what you see in there, okay? This is an example of Russian geology, because by drawing these very lines through here and through there, you can't actually see any of the actual surfaces that are there. So you have to assume that whoever did this interpretation did it correctly, okay? Here, I think you can, if this interpretation is correct, you'll see what looks almost like a channel of some sort, and this is actually just filling it up in terms of things, all right? So kind of curving up towards the end a little bit. And then that's an example of truncation, and again, kind of shown up here with the reflector on top truncating it. All right, and again, these are the types of things that you have to look for each package to get an idea as to whether the sediment is being deposited in a seaward direction, being deposited in a shoreward direction, or is associated with something else. Truncations like this are possibly associated with changes as sea level rises, where you end up having literally a little bit of erosion taking place as sea level rises. Okay. Oh crap! I knew this was going to happen. All right, this is an example of an LST. It's a GIF image that may or may not work. And I'm thinking it's not going to work because every computer is... All right, here we go, okay? So what it's showing you now is a series of images as to what happens when you end up having a low-stand systems tract, okay? You can see the clinoforms being deposited like so, different surfaces being identified, and the nature... Let me go through it again. Alright, so there's the initial phase, and as sea level starts to rise up a little bit again, you have more sediment being deposited on top of it, okay? These will show you the relative positions of where surfaces are going to be, as well as the packages of sediment that are going to be deposited. The other thing I wanted to show you about this particular series of cartoons is this. This is the diagram I tried to show you in terms of how we relate positions of sea level to the actual cartoons being done. They use the sine wave pattern, and they'll show you where the different systems are going to be deposited according to sea level, and then each one of these things has a shift on it showing you where things are relatively speaking. Okay? So there's the start of the low-stand systems tract, just getting the transgression going like so, okay? And it will continue onwards. So this is just the first package of stuff. They have cartoons like this. They have diagrams like this for every possible combination of sea level change. It's based upon what we're finding in the rock record. Okay, so this is all done now in terms of clinoforms being deposited. This is the sequence boundary, so that's the end of the last erosive cycle. All right, high sand systems tract. Again, very quickly to go over this. This is where sea level has reached its maximum level. What's happened in this situation is that you've increased accommodation space. There's usually a backstepping that takes place through here now where the shore face moves inshore. Then we have sediment being deposited back in this direction. All right, and being deposited in the package of sediment like so. So we have this stack, the high stand systems tract, is sitting literally on top of the low stand systems tract like so with surfaces between them. And this one's going to be problematic as well. But again, it shows you how you start stacking things on top of things as well. Now, if this looks like it's entirely non-understandable, I appreciate if you feel that way, because at this stage right now, it is. I've thrown a bunch of things at you now, and right now you've got to get your heads around the whole idea of the difference between a TST and an HST. We have several more lectures where all we're going to do is just sit down and think about what this all means in terms of packages and all. All right? So this type of thing where you start looking at interpreting systems tracts as opposed to sedimentary environments is all linked to this idea of the clinoforms you see here and the patterns that you're looking at. I'll try to give you some examples of actual seismic lines where these have been interpreted. You have to understand, though, these seismic lines are big. And what you end up having is a lot of stuff overlapping. What we really need is to have good seismic lines that show you small portions of stuff that have not already been interpreted. And those are not easy to find right now. Okay? I'm still looking for the ultimate source of these things to show you some pictures of how it all works. All right? Like I said, not the most favorite thing that I have ever done in my life, but is so, so valuable and important. All right, now with this very brief introduction, we're going to do some more sequence stratigraphy on Wednesday. Thursday's lab, I want you to be prepared for this, okay? You're going to be doing seismic interpretations, but not this type of stuff. Like I said, I can't give you this stuff right now because we just don't have enough time to actually do it. Your sequence stratigraphy assignment is going to be using seismic lines to build up basically maps of the subsurface. You'll have 2 weeks to work on this. Your other stuff will come back to you gradually. It's going to take me a long time to get these sections that you've been working on done. I'll try to get them to you by probably next Monday. I'll have the weekend to work on them. And at the end of that little evaluation, somebody's going to get the book prize for best overall package of stuff. Okay.